This video will introduce the sixth chapter of the series of basic knowledge of the spectroelectrochemical method. The third part of optically transparent thin layer spectroelectrochemistry. In the previous article, we introduced the first part of the non-ideal behavior of the Nernst plots, which introduced the spectrally overlapping, chemically uncorrelated redox systems. And in the second part, we will introduce the chemically correlated redox couple. First, the competition between two ligands for a given redox couple is discussed. For many redox, the oxidation or reduction involves the substitution of a ligand, therefore, its equation reduction potential is related to the properties of the ligand. To describe this situation, consider the competition between two ligands for the oxidized form of a given redox couple, where the two reactions have the same electron transfer stoichiometry, in which case the Nernst equation for the above reactions is and. Rewriting the above equations as where Cl1 and Cl2 represent the concentrations of free ligands, the equilibrium reaction between the two oxidation states must exist by subtracting equations above and rearranging them as where the equilibrium constant K for the reaction above can be expressed as under most experimental conditions, the concentration of free ligands are in great excess and can be treated as constants, and the total absorbance at any potential is obtained from Beer's law as and rearranging substituting the equations above into the equation, it can be expressed as from the rearranged equation for the total absorbance at any potential, which alpha can be represented by equation 612. The total concentration OD the redox substances is constant. It can be represented by equation 613 and can be further represented by equation 614. In this case, alpha is equal to substituting the equation 613 into the equation 611, we get the equation 616 which expressed by absorbance. The limiting absorbance of the oxidized and reduced states can be expressed as combining the equations above to the equation 411, the previous fourth chapter, the potential equation for reversible reaction. In the case where Cl1 and Cl2 are substantially over C*, the Nernst plot is still linear, but it should be noted that the resulting intercept moment is not the E10 line value of the potential due to the extra term on the right side of the equation in equation 620. Considering the processes containing two consecutive electron transfers, it can be expressed as the following reaction equilibrium. When the potential according to the real state, when the equilibrium is reached, there are two concentration relationships, which E1 represents the potential for the equilibrium of the oxidized state to the intermediate state reaction, and E2 represents the potential for the equilibrium of the intermediate state to the reduced reaction. Since the co-total concentrations remains constant, it can be expressed as the absorbance at a given wavelength can be expressed by the equation 625, where epsilon is the absorbance coefficient of the substance. Substituting AE in the numerator part of formula 411, with formula 627, and substituting AE in the denominator part with formula 626 to get the 630. Then the Cp in the numerator part is extracted and the Cr in the denominator part is extracted to obtain equation 631. Substituting the equations 622, 623 into equation 631 and simplify to obtain. In this way, the concentration ratio of each component in the equations 631 is obtained by using an appropriate potential and concentration ratio. For convenience, the following dimensionless variables are used. Take a log of both sides of equation 632, to get the equation 638, which will be mentioned later. It is important to use different systems to compare the system and data values for several representative Nernst plots. Figure 6.1 shows several representative Nernst plots using different values of θ1 per θ2 and delta. For curves B and C, the slope of the curve decreases from 1 at smaller x, and passes through a very small value, and then increases to 1 at larger x values. Curve E showed, when the slope increases from 1 through an extreme value and then decreases to 1. Curve D represents the special case, where the slope remains constant with a value of 1. For the case where the absorption coefficient of the intermediate state is equal to that of 0, the slope of the Nernst diagram is connected from 1 with the smaller value of x. Curve A, increase to 2 when the value of z is larger. For the case where the absorption coefficient of intermediate state is equal to that of reduced state, the slope decreases continuously from 2 to 1, which is represented by curve F. The slope of the Nernst plot is expressed by the differential equation 639. By differential equation 639, the value at the inflection point B of the curve B of the Nernst plot is: as x tends to 0, the Nernst plot converges to the asymptote A, with slope 1. When x tends to infinite, the asymptote is. The intersection of the two asymptotes on the horizontal line are showed as the points A and C. The values of theta, ln theta, and delta can be estimated from the experimentally determined values of the potential at the inflection point plus the values of the two intercepts of the experimental asymptote. Figure 6.3 shows the Nernst plots of 1 millimolar gold squaret anion in 0.5 molar tetraethylammonium perchlorate in dimethylformamide solution at 362 and 364 nanometer. Through the experimental points, the curves were calculated by equation 638. With E1 equal -0.104 volts, E2 equal -0.249 volts and the values of delta at different wavelengths. The potential and delta values are first estimated by the above graphing method, and then their exact values are obtained by least squares regression. This concludes the 6th chapter of the series on the basic knowledge of the spectroelectrochemical method, the third part of optically transparent thin layer spectroelectrochemistry.